Okay, in this video, I'm going to go through A-level Chemistry, Edexcel A-level Chemistry Paper 3. This is the June 2018 paper, and I'm going to do the second half of the paper, starting at question 6. I covered questions 1 to 5 in an earlier video. Okay, so the question 6 then. Question is about the analysis of an unknown carboxylic acid X by 3 students. The students analyzed and found the molecular ion peak is 116, so that means the MR of the compound is 116. They proposed 3 different structures, and if you check the MRs of them, they're all, even though they've got different molecular formula and different structural formulas, they've all got the same MR of 116. Now, they're also given the infrared spectrum of X. State 2 wave number ranges that provide evidence that the compound is a carboxylic acid. Right, so carboxylic acid contains the carbonyl, okay, and the OH. Now, if you look here, carbonyl, carbon double bond O, carboxylic acid, alkyl carbonyls, 1725 to 1700 centimeters to the -1. Okay, for that one. And you've also got the OH in a carboxylic acid, which is different to the OH in alcohol. So the wave number range there is 3,300 to 2,500 centimeters to the -1. And that will be a pretty broad peak as well. Okay, right. So that's it. Next bit, one of the students suggests that the infrared spectrum and the data in the data booklet alone could be used to identify which structure is X. Show these correct, right? So let's have a look at that. Now, if we think, let's look at if it was structure 1. Okay, if it's structure 1, you are going to get the characteristic alcohol. The carboxylic acid OH. You're going to see that, and you're going to see the carbonyl for an alkyl carboxylic acid around there, but also you're going to get an absorbance for the double bond, which is about 1700. Where's it gone? CC. Okay, yeah, it's about there. Okay, so you would see that. Now, how could you distinguish 1 from 2? Because of course 2 is going to show you the characteristic absorbances for the carboxylic acid and for the carbonyl, and for the carbon-carbon, but you're also going to get the OH, the hydroxide group for an alcohol, which is different. It's in that range there. It's further to the left. Okay, so you would be able to distinguish 1 and 2. I'll just talk about 1 and 2 in a minute. 1 and 2 would be 2 would be a bit tricky because I've just pasted in these pictures. Right, this is, you've got a carboxylic acid and an alcohol. Now, if you just got a carboxylic acid, you get, that's the peak for the OH, carboxylic acid. For an alcohol, the OH peak is there. So when you've got both, you get this funny distorted, they overlap a bit, but you can tell that is not a proper carboxylic acid OH. You've got an alcohol one in there as well. It's a bit, the shape isn't quite right, and look at the wave ranges. Okay, so that would be a bit tricky, but you would be able to tell it. And then of course the last one would be quite easy to tell if you had the last one, because you would have the carboxylic acid absorbances, but you'd not have any, you wouldn't have the CC the C double bond C absorbance there. Okay. Okay, so the students decided to carry an acid-base titration out to obtain further information about X. Each student uses solid sodium hydroxide to prepare a solution of concentration. That concentration. Calculate the mass of sodium hydroxide the student should use to prepare 250 centimeters cubed of solution. So what you need to do first of all, of course, is you need to write down the moles of NaOH is going to be the concentration times by the volume. The concentration is, sorry about that, 0.14, and the volume is 0.25 dm cubed, so that is equal to 0.035 moles. Okay, now the next thing we need to do is we need to work out the mass. The mass is equal to the moles times by the MR. So the moles, we have 0.035, and the MR of NaOH is 40. So that times by 40 gives us 1.40 grams. That's pretty straightforward, really. Okay, next part of the question then. All right, so this is what the students did. So there's a bit of detail here, okay? So each of the students makes up the standard sodium hydroxide solution and titrates this against with the same solution of X of known concentration. So they all put the sodium hydroxide into the burette, into the conical flask, and they're going to titrate into that the solution of X, the acid. Right, the student A correctly prepares it, fills the burette, carries out the titration, repeats, and gets a concordant result of 10.2. He does it right. Okay, now student B makes a bit of a mistake here because he gets his volumetric flask and he's making it up. There's the mark. And he notices when he's filled it up that he goes over the mark, it says there, and so he just throws away that extra bit. Okay, so he discards the extra bit. Of course, that's not going to help because this NaOH is too dilute. It's more dilute than he thinks it is, and we'll talk about that in the next question, I think. Student C, he did it right, but he does his he pipettes his sodium hydroxide into a wet conical flask. Okay, that was wet. But we'll see that as a question. Does that matter? No, it doesn't. We'll see why. We'll answer that question in a minute. Explain how student B affects the value of the titer. Well, his NaOH is too dilute. We've established that. So that means you are not going to need as much X. So the titer of X will be smaller than it should be, than the true value. Okay, because this sodium hydroxide is too dilute. And now the next question, explain how student C's use of a wet conical flask affects the value of the titer. It won't affect it at all because the moles of NaOH, it's the moles that he's added to this conical flask that's important. And the moles of NaOH is dependent on the conc of the NaOH he's added, which is correct, and the volume, which is 10 centimeters cubed. So he's got, having water in there, doesn't change the number of moles of sodium hydroxide, so that it will still be the same number of moles of the acid to neutralize it. So the titer will be absolutely fine. Okay, right. Now we're talking about errors. Student A uses 3 pieces of apparatus to measure the volumes. The burette has an uncertainty of, so we've got to calculate which volume has the lowest percentage uncertainty. So let's do it for each of them. Right, the burette, we had a titer of 10.2, if you read early in the question there. Now the error is 0.05 for each volume reading, but we do 2 volume readings, one to measure the start volume and then the reading in the burette when you've finished the titration. So we have got 2 times 0.05 centimeters cubed over the volume measured, 10.2 times 100. That is equal to, I think it's about 1%. At 0.98%, okay, for that one. The volumetric flask, well, he's got an uncertainty of 0.3, so that is going to be, just rub that out there. The volumetric is going to be 0.3 over 250. It's going to be absolutely tiny, times 100. 0.12%, and that is going to be the lowest one. Let's calculate the pipette as well. So that is out by 0.04. It's just one measurement reading there, so it's 0.04 over 10 times 100. That's equal to 0.4%. Okay, so the lowest uncertainty is the volumetric flask, this one here. It's important there to remember for the burette you do 2 times that. They're pretty keen on that because you take 2 measurements, initial reading and final reading. Okay, student A calculates the correct value for the molar mass of X using the titration results, and the results indicate X has structure 1. Okay, so it's a dicarboxylic acid, yeah. Okay, write an equation for the reaction between structure 1 and the sodium hydroxide solution. Okay, so let's write it the way that they have written it in the question. And we're going to react that with sodium hydroxide. Now, you're going to need 2 moles of sodium hydroxide because you've got 2 protons. Diprotic acid is going to take that proton and that one. Okay, so we are going to end up with now I'm going to write it down like this: NaOCCH and we're going to have 2 waters because each OH picks up 1 proton. I don't really like writing formulae like that because it kind of gives the impression that the Na is covalently bonded to the O, whereas of course it's definitely not, but they don't mind you writing it like that. Or if you, I really prefer to write that as Na plus and do that there. Either one's acceptable. Okay, the students could have identified the 3 structures using chemical tests. Complete the table to show which would react with bromine water or when heated with acidified potassium dichromate. Right, test of bromine water obviously detects double bonds and decolorizes it. So these 2 will decolorize the bromine water, and that one it won't react. No reaction. The bromine water will stay red, already brown. Now, potassium dichromate, of course, doesn't ask you what happens, but potassium dichromate is an oxidizing agent, and it can oxidize alcohols, primary and secondary alcohols. It can't touch carboxylic acid. So the only one that's going to react there is going to be this one. Okay, and these 2 will not react with it. And the color change, it doesn't ask you what it is, but it goes from orange dichromate to green chromium 3. So you get an orange-green color change with the alcohol, but not with the other 2 because there's nothing there that can be oxidized by it. Okay, right, stereoisomerism. Right, so it says this dicarboxylic acid has 2 stereoisomers. Draw the structures of these, okay, the E and the Z. So put our double bond down first, and you can see attached to this carbon we have got an H, and we've got a carboxylic acid. And so that one, we've got the 2 high priority groups. It simply is the heaviest things, isn't it? These are the 2 high priority groups on the same side, so that is the Z isomer. And the E isomer, all we've got to do is have the 2 priority groups on opposite sides, so it's going to be like that. Okay, it's a good idea to show draw them out. The bond angle here is all 120, and I've drawn the bond angles are about 120, and you can see clearly the stereochemistry there. Okay, so that's going to be the E isomer. Right. And the next question, why does it show EZ isomerism? Now, normally it's a 1 mark question, but it's 2 here. So normally I would just say no rotation about double bond. Because it's 2 marks, I think you also need to say because 2 different groups attached to the carbons, to both carbons. Let's see, both carbons. forming the double bond. Yeah, I think you need to say that second point there, okay, because it is a 2-mark question. Of course, just to say what I mean there, if, for example, you had that was these two are the same, then there's no possibility to have EZ isomerism then, is there? Okay, right. So on to question 7. This is about weak acids. Okay, now here they've got a weak acid HX, and what are they adding to it? They say they're adding sodium hydroxide. Now you should know when you start adding sodium hydroxide to weak acid, you make some. So you're going to turn some of the weak acid into the conjugate base, and so that means you've essentially got a buffer solution. So there, you've got to start thinking with your buffer solution calculation head for this question. Okay, so what I would do here is whenever we do a buffer calculation, we rearrange our Ka expression. So make H plus the subject. We're going to get Ka is equal to what's Hx. They're calling it in this question, not Ha. So concentration of the weak acid divided by the concentration of its conjugate base. We're always going to do that. Okay. Now let's start off with HX, and at HX, and they're going to add some sodium hydroxide to that, and I'm just going to write the OH minus sign there. That's going to react with HX. It's going to remove a proton from it, so you're going to get the conjugate base, and you're going to get water. I'm going to put down here the start moles of HX and the final moles of HX, and then I'm going to put the final of all of them, the final concentration. Now when we get the final concentration of HX and AX minus, we're going to put them into our expression here, and we can work out H plus and work out the pH. Okay, so that's what we're going to do here. So let's read the question. It says a solution formed by mixing, we've got 10 centimeters cubed of 0.8 molar sodium hydroxide. So the moles NaOH at the start is going to be concentration, so OH moles, I'll just write it up here, is equal to conc times volume. The concentration is 0.8 multiplied by the volume, 10.5 over 1,000. That gives us 8.0084. Okay, let's write that down there. Moles HX, we do the same thing with HX. So HX, where have we gone for that? 25 is the volume of the HX and 0.9 is the concentration. So moles HX, conc times volume, 0.92 multiplied by 25 over 1,000. That is equal to 0.023. So I'm going to put that number into there, 0.023. Now, final moles. So, right, we're going to presume all of the OH minus will react with the acid, so we've got none left. Not quite true. There'll always be a tiny bit left. You always have some OH minus in solution, but ignore that. So we're going to do 0.023 minus 0.0084, and that is going to give us 0.0146 moles of HX. How many moles of X minus have we got? Well, for every 1 mole of OH minus in there, we're going to make 1 mole of that. So that's going to be 0.0084. Now, the final concentration, right, we do know the volume there. It's going to be 25 plus 10.5, but we don't need to bother with that because we're just going to call it V, and the V will cancel out in the expression. So, but I will make a point of writing that down and not just ignoring it, over V. 0.00, that's the concentration over V. Now we're ready to put these values into our equation up here. So let's do that. H plus concentration is going to be equal to the Ka, which we are told is 5.25 times 10 to the minus 5, multiplied by the concentration of Hx, which is 0.0146 over V, and the X minus is 0.0084 over V. Our V's are going to cancel out. Put the numbers into the calculator and we get 9.125 times 10 to the minus 5 is the concentration of H plus ions. Mole per decimeter cubed. Take a minus log of that to get the pH. Give it to 2 decimal places. We get 4.04 is our answer there. Okay, so it's a buffer calculation and quite a difficult one. The other way of making a buffer, of course, is by not adding OH minus, is by mixing up directly. If you have, H, the acid, and you've got a sodium salt of it available, and those sort of buffer calculations are a bit easier. But that's quite a tricky one, but pretty standard though. Okay, propanoic acid is a weak acid. On the grid below, sketch the change in pH during the addition of. So we've got that much sodium hydroxide we're going to add to that many propanoic acid. Now you can see we're same concentration of both, so that means the end point is going to come at 25. That's where our end point is going to be, and they're going to go past the end point. We're going to carry on adding more sodium hydroxide. So we've got to draw a titration curve, right? So it will be something like this. Okay, so I'm going to draw it. So it's got to be the endpoints there. That's the vertical bit. Now the endpoint of a weak acid, weak base is always a bit alkaline. So I shouldn't I'm going to leave that being alkaline and get a bit of a S-shaped curve like that. So you see my endpoint there is probably about 8.5, maybe 9 even. Okay. Which is right, it shouldn't be at 7, and then that's going to tail off like that up at the top. Okay, so 2 important points there. You need your endpoint in the right place, and the endpoint has got to be in the right pH range, which is slightly alkaline. Okay, then explain how we'd use your graph to obtain the value of the acid dissociation constant for Ka. Right, so going back to our buffer calculation, we know that we will say that H plus is equal to Ka HA over A minus. Now when HA conc is equal to A minus concentration, then H plus is equal to, that fraction becomes 1, is equal to Ka. Take minus logs of both sides of the equation, we get pH is equal to pKa, the minus log of the Ka. Okay, now when is HA concentration equal to A minus? That's our half equivalence point, which in this case is going to be 12.5 centimeters, because it's 25 is the equivalence point, so it's here. So 12.5 about there. So I'm going to draw a construction line. What you do is you do that. Now you know at half equivalence point, the pH is equal to the pKa. So we know that is the pKa of the weak acid there at 6. And then we work out Ka by just doing Ka is equal to 10 to the power of minus pKa, the anti-log of that there. Okay, so that's how you do it. Half equivalence point, and again, that's a pretty standard thing to know, but a lot of people won't know it. Okay, so that's that question done there. Okay, question 8 now, which is a long question about how to determine an equilibrium constant for this esterification reaction. So we've got ethanoic acid and an alcohol, propan-1-ol, forming propyl ethanoate and water. So what are we doing here? They mix, they tell us here. We start off with just the ethanoic acid and water. Sorry, it's just ethanoic acid and the propanol. We haven't got any ester, but we do have some water. And they also add a bit of hydrochloric acid, and they ask what that is for in the next question, and it's a catalyst. That's what it's for, and again, you should know that. Right. They leave the mixture for a week. Here. Then they get the equilibrium mixture and they put it into a 250 volumetric flask. And they take 25 centimeters cubed of that out for titration. Put that into a conical flask. And they titrate it with sodium hydroxide, which will react with the acid in there. Okay, so which acids have we got in there? We have to be careful because we're going to have ethanoic acid, but we've also got some of the hydrochloric acid, which they added as the catalyst. So we're going to have to, so that we can work out the number of moles of H plus in there, and move on from there. We'll talk about that now. Okay, so question 1, it says state the role of the hydrochloric acid. Well, that is to act as a catalyst, as we said. Calculate the total amount in moles of acid present in the volumetric flask. Right, so how are we going to do that? Right, we've got the NaOH there, and it tells us that we need 23.6 of that in the titration, and the concentration of that is 0.2. So moles of NaOH added required in the titration is conc times volume. So it's 0.2 times 23.6 over 1,000, which gives us 4.72 times 10 to the minus 3. Okay. Now, OH minus and H plus react in a 1-to-1 ratio. So the moles H plus in 25 is going to be the same as that. 4.72 times 10 to the minus 3. But that is only a tenth of what we had originally. This is a 250 volumetric flask here with the equilibrium mixture. And we only took 25 of that out. So the moles of H plus in the equilibrium mixture is going to be 10 times that. Moles H plus in the whole of the equilibrium mixture. Multiply that by 10, 0.0472 moles. Okay, so that's the answer there, 0.0472 moles. Right, now next it tells us the dilute hydrochloric acid, well, that contained 0.04. So we're gonna how many moles of ethanoic have we got then? So total moles of acid is that much. Moles of H plus from HCl, we are told, is 0.004. So the moles of ethanoic acid is going to be the total moles of acid minus the moles of HCl. They're both monoprotic acids, of course, so we don't do moles of acid the same as the moles of H plus. And that is going to give us, do that subtraction, 0.0, what is it? 0.0432. Okay, so we've done that. Now, it's going to talk us through how to find the other ones. I'm going to draw a little table in a minute. Okay, so the initial mixture in the boiling tube contained 0.015 moles of ethanoic acid. They tell us that. So use your answer to B to calculate the moles that reacted to form the ester. So we've got, that's how much we've got left over. We started off with that, so it's a subtraction. So moles of ethanoic acid reacted. That is equal to 0.0432 minus 0.105. Sorry, the other way around, sorry. which gives us, how does that give us? 0.0618. Okay, that's how many moles are reacted. Now, it kind of says then, use the information in the method and your answer to calculate the amounts in moles of propanol, propyl ethanoate, and water that are present. So I would do one of these tables. Most people use these sort of tables. So if you read the question, we started off with this many moles of ethanoic, that many moles of propanol, that many moles of water, and no ester. The moles of ethanoic acid used up, we just worked out, was 0.0618. Now, for every mole of ethanoic we must use up 1 mole of propanol. They will react in a 1-to-1 ratio, so it's 0.0618 of that used up. So let's fill in the amount that's left over then. So the amount that's left over is, well, we worked that one out anyway previously, 0.432. How much propanol have we got left? So we've got to take away 0.0618 from 0.08. That gives us 0.0182. Right, now if we've used up that many moles of propanol, we have made that many, the same mole, every time we use up a mole of propanol, or we're going to make 1 mole of ester. So the moles of ester at the end is that 0.618, and we're going to make that many moles of water as well. So the moles of water at equilibrium is the original moles plus the extra water we've made, and that gives us 0.1728. So here we have found out the equilibrium moles of all 4 components, all 4. Now, okay. Now the next bit, obviously, of this question is they're going to ask you to write the equilibrium expression and put these numbers into it. Okay, so let's do that. Write the equilibrium expression. Right, I'm just to keep things quick, I'm just going to not write down the full formula. I'm going to write ester, concentration of ester, concentration of water over the concentration of the acid, ethanoic acid, and the concentration of the propanol. Right, now it then says here why it is possible in this case to calculate Kc using moles rather than equilibrium concentrations. Right, now the reason why you can do that is because what we can say here is the equilibrium concentration of that, we don't know the volume, but we can call the volume V, and the V's will cancel out. Okay, so that's going to be 0.042 over V. That's going to be that over V, over V, over V with the volume. Let's put the numbers in there then. So we're going to get, we've got moles of water, ester, sorry, 0.0618 over V, multiplied by 0.1728 over V, divided by 0.0432 over V times 0.0182 over V. Now, because we've got the same number of moles on both sides of the equation, so you'll probably say that in your answer, because you've got the same number of moles, those volumes will all cancel out. That's not the case if you have different number of moles, okay? And another way of doing this, of course, this is going to have no units, this equilibrium constant, yeah? And because you've got the same number of moles, whenever you've got that, then the volumes will always cancel out. Okay, so we've answered that question. Why is it possible to do that? And now we've got to put the numbers in to actually work out a value and give it to the appropriate number of figs. So you put that in there. Right, so I'm just going to work out that in the calculator. You get, that comes to 13.58 on your calculator, but and there's no units. But let's think about the correct number of significant figures. Well, all the data is given to 3 significant figures, so we should give this to 3, not 4. So 13.6 would be the correct answer. Okay, so like that. Now, the pink color of the phenolphthalein fades after the endpoint of this titration. Possible explanation. Right, phenolphthalein, of course, it's pink in alkali, colorless in acid or neutral. So for some reason the solution after the endpoint of the titration becomes more acidic. And there's two possible explanations for that. It absorbs a bit of carbon dioxide from the atmosphere, which is a bit acidic. That's one possibility. Or in this case, because you've got an equilibrium reaction here, what we're doing is we've obviously got our ester plus water, and it can give us the acid and the alcohol. So yeah, you've got ester in there, and what you're doing is you are removing the carboxylic acid by adding NaOH. So that's going to shift the position of the equilibrium there. If you keep removing the acid, it's going to shift forward to try and restore the balance, and so it's going to make more acid. So either one of those, I think they allow. So the ester starts hydrolyzing because you've shifted the position of equilibrium, making acid, or you can say it's just CO2 from the atmosphere. Right, here, I think it's the last question. All right, explain what you could do to confirm that 1 week is sufficient time for the mixture to reach equilibrium. Well, you could leave it for a week, and then you could do another one and do that 2 weeks, and you should, if it's 1 week is the same, you should get the same value for case C, whether you leave it for 1 week or not. Okay. A student repeated the experiment but left the mixture in a water bath at 40 degrees C. Okay. Right, so the temperature is higher, and here we have got they tell us that this is endothermic because it's positive. Okay, so if we increase the temperature, Le Chatelier tells us that the reaction will move in the endo direction. In this case, it's going to move forward. So we're going to get more products, and Kc, of course, is equal to its concentration of the products over the reactants. The product is going to get bigger, concentration is going to products bigger, concentration of reactants smaller, so Kc will get bigger. That's what will happen there. Okay. Right, and that is the end of the paper.